Hello, I'm Mike McCormick of AIQ. This video clip is to introduce the Insight M700 system and its user interface, and it describes the system's potential to capture and locate those elusive and transient faults that are very disruptive to both customers and operators. So just a recap of AIQ, it's the outcome of a collaboration between leading engineers in the European power industry, and the Insight range of products and software is the result of this collaboration. The solutions we deliver have been designed to enhance the networks in the face of major challenges, for example, the onset of distributed generation. As part of the design process, AIQ has developed high earth fault sensitivity of better than 10 kiloohms, supported by synchronized data of better than 1 microsecond resolution, all packaged in robust and reliable product designs. Our technologies deliver major enhancements to the safety, reliability and efficiency of the networks with a focus on improved safety. So let's take a look at the M700 itself. The M700 is a portable system designed for temporary installation that is used to capture faults and transient activity that are being experienced on a particular feeder that are causing customer outages and proving very difficult to locate. The first component of the system is the S700, which is installed in the substation. The S700 is a part of the Insight range of products with unique features in sensitive earth fault detection of better than 10 kiloohms, and the device delivers head of feeder phase current, amplitude and phase, and zero sequence current with zero sequence voltage. The S700 monitors continuously for fault activity, delivering all of its synchronized data to a hosted server for processing by the M700 application. The M700 also has line nodes that are installed along the feeder upstream and downstream of where the fault is suspected to be. This diagram shows 3 of these nodes, but the customer can select the number they require, 2, 3 or 4. The line node captures transients, faults and disturbances and sends the data to the server for processing. Because these nodes are synchronized to GPS, all data from the substation and line is time coherent, giving a snapshot picture of all fault activity within an alignment of 1 microsecond. The equipment comes in robust portable carry cases for storage and transport to the field. The installed line sensors are powered by the line, provided there is a minimum of 3 amps of line load, and also has a solar panel. The data concentrator, L700, has a battery that will keep the device active for 20 days. A mains battery charger is also supplied with the kit. So now let's look at the GUI itself. In the GUI homepage, the center panel is a model of the network showing the substation node and the 3 line nodes. On the left panel are faults that have been captured by the M700, and on the right panel are the real-time alarms of the devices installed. This is the basic information provided by the system, but the user can drill into the characteristics of individual faults. First, we are going to look at a fault in a resistance earth network which has been successfully captured by the M700. This is a radial network, and the fault characteristics have determined that the fault passed through nodes S and L1, but not L2. Therefore, the graphic confirms the fault has occurred between L1 and L2. We are now going to look into the fault, and what we're looking at first is the substation node. This is simply done by double-clicking on the node in the network diagram. A screen appears showing the fault current magnitude and phase. By moving the cursor to the time when the fault has occurred, we can see the vector diagram that the fault magnitude is 55 amps. Looking at the waveforms, we can clearly see that this is an A phase to earth fault which has cleared within 3 cycles. Then looking at the same fault, but in this instance in the line node location L1, you can see the same fault characteristics as we're seeing in the substation, for both the magnitude and phase, which are also shown in the waveforms. This clearly shows that the fault is downstream of L1. Because the M700 operates in isolated, compensated and resistance earth systems, we are now looking at another fault, in this case on an isolated network. You will see that all nodes are reporting due to the presence of zero sequence current, but you can also see that the M700 has identified the faulted section as being between L1 and L2 where the line is flashing. In this instance, we are looking at the L1 fault characteristics, and because it is in an isolated network, we are looking specifically at the zero sequence values. From that, we can see L1 has seen the fault with a small current magnitude shown at 5 amps, with a phase angle at 0 degrees. This technique is specific to an isolated network and is enabled by accurate time synchronization between the sensors. Now, if we look deeper into the transient waveform, we can observe that there is minimal change in current due to the fault. However, by extracting the active and reactive components of the fault, we can use them for comparison with the measurements at the other nodes, thereby determining with clarity whether the node is upstream or downstream of the fault. So now, having looked at L1, we will look at L2, which is at the other side of the fault. You can see from the zero sequence waveform that the magnitude is 3.7 amps with a phase angle of 162 degrees. This is in comparison to L1, which was 5 amps and 0 degrees. This difference in the characteristics confirms that the fault was seen at L1 but not seen at L2. This is the fundamental principle of fault detection in an isolated network. The screen gives you an indication of the level of detail that is available both graphically and to the server for additional processing. In order to understand the relationship between the nodes more clearly, we can click on View Details. This displays all nodes simultaneously, and the detail here shows the complete picture of the line at the time of fault and underpins the accuracy of the graphics that simply show the location of the fault. When you observe the different nodes, you will see that the zero sequence currents captured at S node and L1 node are in phase, but it changes significantly at L2, which is downstream of the fault. This is a high-level overview of the M700, and the team at AIQ are happy to answer any questions that you may have about the M700 or any of the Insight products. The portability of the equipment is enhanced by plug and play to the user interface, which is a hosted service, so that there is virtually no setup required, and it is ready and able to find and analyze those elusive faults quickly and accurately. In addition to the fault location aspects of the M700, it is a very useful tool for training in network fault behavior, and it is an excellent fault visualization tool. Thank you very much for your time, and if we can be of service to you, please do not hesitate to visit the Ask the Expert section of our website with any queries you may have.